So I started the recording at this point, and again, good morning and thanks for your time. What we're looking at is the interface to Spartan, and this is essentially what you would see on your screen if you double click on the Spartan icon. The interface will open up, and it's sort of in a static mode. The background is kind of this soft green color that tends to allow graphical models of molecules to stand out once they're rendered in 3D. So as an intro, I would say that what we'll try and cover today are three areas, three main components of Spartan. The first will be the building or the construction of molecules, and we will do that in 2D. We will also do that in 3D, and in the 3D component, which is really one of the strengths of Spartan, 3D visualization, there are a number of tabbed model kits that are available as far as building in 3D. So we'll look at an organic model kit, an inorganic model kit, and also a peptide and a nucleotide builder. And there's even a substituent builder if you wanted to sort of construct a scaffold and then generate a virtual library based on substituting not necessarily at a specific point with an atom or a group, but with a definition of groups. So if I wanted to put, for example, an electron withdrawing group at a specific location, or if I wanted to put an aromatic group at a specific location, I can define what that group means, and then I can elaborate that and essentially draw out a large list of dozens to hundreds to even thousands of molecules based on substitution. So I'll show the substituent builder as well. So once we've covered the building piece, I'll also point to the file menu, which is really the other way that you can get models into Spartan. We read a number of common molecular file formats. We also read SMILE strings, and we read INCHI strings. So there's lots of ways to get things in Spartan. So we'll focus on the building, the constructing, and then maybe the importing. The next thing we'll look at is visualization. So one of the strengths of Spartan is definitely 3D visualization. We will look at visualization of data. We'll look at visualization of some calculated graphical models, whether those be the electron density or the electrostatic potential map or molecular orbitals. I'll show you where those are and how they're accessed within the program and how you would request those. And the final thing we'll do is we'll run a couple of quantum chemical calculations. I'll introduce you to the calculations dialog, which is really the sort of the control center for setting up calculations. And I won't run anything that's going to take an extended period of time, just in the interest of our time. But I'll point to where the computational models are and show you that they're organized hierarchically, essentially from the fastest and perhaps least accurate to the more accurate and definitely slower as far as computer time is concerned models. So we sort of scan the gamut from calculations that can take less than a second or a few seconds to things that can take minutes to several hours, which is sort of routine and I would say sort of bumps up against what I would consider practical. And then there are certainly jobs that can take overnight or several days, depending on the computational model that you choose and the size of the basis set that you choose. So once we've done that, I will have shown the majority of the interface. And I think what we'll do is probably wrap there. And then, as I said, I'll be happy to take questions offline. So the three main goals will be building visualization and importing, looking at the visuals as far as models and graphical models, and then setting up specific calculations. And we'll look at the results both in output as far as text output is concerned, but also in a couple of different ways that Spartan can analyze output or data, and those will be the properties dialog, and we'll look at the spreadsheet as well. Okay, so I'm going to go ahead and get started with the 2D building, and I'll point to the top of the screen, the top left side. You'll see there's a file menu, And essentially, when you open the program, if there's nothing on screen, you don't have anything to begin with, you haven't opened a document, but just open the application, a number of things will be grayed out until you actually have a file available. So file menu, new build will pull us into 3D, but I'm going to go first to 2D, and I'm going to do new sketch. New sketch will open up essentially an alternate rendering of the interface that's a 2D set of tools for building. And let me just build something simple. Let me take a look here. I'll build a quick model of maybe salicylic acid, for example. You'll see that the 2D builder is sort of arranged the organic portion of the periodic table. So we've got boron, carbon, nitrogen, oxygen, fluorine, the set of halogens underneath fluorine, and just a few elements are available. There is this more button, which will open up essentially the rest of the periodic table, also some functional groups, and some organometallics, and I can just show that briefly. I won't go into a lot of detail on this, but the rest of the periodic table, a set of groups, and then a set of ligands for building organometallics. The 2D builder is fairly new to Spartan. We introduced it first in Spartan 14, so it really only goes back about 5 years at this point, but it's had a couple of revisions with Spartan 16 and Spartan 18, so we're pretty comfortable with it. But if you have any questions on using it, again, after the presentation, I'll be happy to take those. So I said we build salicylic acid. I can do that by simply selecting an aromatic ring up here, benzene. The first build motion is a double click. So if I double click on screen, I'll insert a benzene molecule. There are a couple of groups here as well. So I'm going to grab the carbonyl or carboxylic acid functionality rather, and I'm just going to simply click on a location, drag out, and release, and that will modify the benzene to benzoic acid, and then let me just put a hydroxy group adjacent. Okay, and then once I've done that, really the sketch mode is intended sort of as a one-shot building tool. The bulk of the work in Spartan is done in 3D. So if I go up here to this icon that looks like a pair of glasses, we call them the Harry Potter glasses. That references view, and when you click on that, will automatically convert what I've built in 2D into 3D. Now, if I made a mistake and I wanted to modify something and needed to go back, I can either, under the build menu, go back to edit sketch, or there's a set of icons that are on essentially permanent display, and the edit sketch is one of those. So if I click on that, that will drop me back into the 2D rendering. But this is salicylic acid. We can see that and recognize that sort of just based on our background. But I will reference that Spartan interfaces a database with the Spartan 18 parallel suite, which is something on the order of 305,000 pre-built and pre-calculated structures. And those come from two different density functional models. But essentially, anytime you see a name down here in the lower right of the interface, that's just a sort of an announcement that this particular molecule exists. And if I wanted to retrieve it from a database, I could do so. This is a shortcut to the database that we call the SSPD, which stands for the Spartan Spectra and Properties Database. I won't go more into that now, but I'll reference the database again when we look at graphical models. We'll pull some things back before running calculations so that we can render some calculated graphical models. Okay, so now that I have something in 3D, we can do a number of things with it. The first point to mention is I've got a ball and spoke model is the default model that we render in Spartan. You can certainly change that if you like. But for the time being, let's look at this as a ball and spoke model. if you wanted to modify that, if you go under the model menu, which is in the upper left corner, you'll see there's wire, ball and wire, tube, ball and spoke, which is the default, space filling. There's a line rendering, which is a sort of a 2D equivalent, but for visualizing in 3D. And then there's this entry that says hide. And at first, hide seems a little bit unobvious why one would want to hide something. But if you're looking at a biopolymer or some macromolecular structure, for example, from the PDB, we may want to essentially just render that with its secondary or tertiary background structure in ribbon mode, and hide the actual molecular structure or the atoms involved. So that's what the hide is about. So just to give you an idea, you can render in multiple model styles. I'll just show you that. Here's the space filling model, etc. Okay, in 3D we can do a number of things. I can go in and I can measure distances, angles, and dihedrals. That's referenced under the or accessed under the geometry menu, which is immediately to the right of the model menu. And you'll see there's a set of icons at the top that are for measured distance, angle, and dihedral. So if I wanted to measure, for example, the distance between this oxygen and this hydrogen, or if you could also do the same, you'll see that the distance is rendered in the lower right corner. You could also do the same thing by clicking on a bond length. That will also give a distance between the atoms that the bond is defined by. Things don't need to be bonded, so if I wanted to measure, for example, the distance between this hydroxy proton out here and this other one, I could certainly do that. And you'll note this in the lower right region of the interface. That's a place where a lot of data will appear based on context. So when I'm measuring things, for example, we'll see that. Also, when I show you later on in a molecular orbital diagram, if I actually click on a specific molecular orbital, I'll, for example, get its orbital energy will appear in the lower right corner. And it will often be accompanied by this icon, which is basically, it's intended to give a graphical representation of posting. So it's a little downward yellow arrow, and it's I don't know if it's supposed to be a post-it note or what, but that's our post icon. And you'll see that throughout the interface in a number of dialogues. So anytime you see that, if you click on that icon, that will actually post the data value into our spreadsheet. I'm getting a little ahead of myself, but I'll just show you where that is, the spreadsheet. I clicked on the spreadsheet icon, and you'll see, hey, the distance between hydrogen 15 and 16 is here, and here's that distance. So I posted that into the spreadsheet. Okay, so that's an example of measuring distance. The same would be true if I wanted to measure an angle, for example. The angle that defines this hydroxy group here, right now it's at 108.8 degrees. I haven't done any optimization or minimization of structure at all. At this point, all I've done is built it. And so these would be the default angles from the retrieval from 2D to 3D. And again, that post button is highlighted to reference. I could post that into the spreadsheet. Same is true if rather than clicking on 3 atoms, one could click on just 2 bonds. So if I wanted to, for example, I'm not actually clicking on the atom, but I'm just clicking on the single bond here and this double bond here. That's another way of referencing an angle. We could do the same thing with dihedral angle. That will require either 3 bonds or 4 atoms. So I could click 1, 2, 3, 4 to get the dihedral angle here, or I could do the same if I move over here and just click on 3 bonds. If I do 1, 2, and 3. So measuring distance, angle, and dihedral is fairly straightforward. Let me point out another visualization tool under, once we're in 3D. If you go under the model menu, we looked at the different model styles that were available. I'll just point to a couple of other things that one can do. one can turn on and turn off hydrogens. Not typically familiar necessarily in ball and spoke, but you've probably all seen under a tube rendering style images like this where hydrogens are suppressed just to make the model a bit simpler to process visually, especially if you've got a larger system. So one can hide the hydrogens. One can also, let me turn this back on, under the model menu, one can also turn on a display of hydrogen bonding. So if I click on hydrogen bonds, I'll see that I've got a nice, essentially a intramolecular hydrogen bond here between this hydroxy group and this carbonyl oxygen. This would display as well had we, had a number of perhaps water molecules or molecules that surround this. If I'm looking at a dimer or something that's complex, you'll often see intermolecular hydrogen bonding as well. So intra and intramolecular hydrogen bonding are visualized by this little dotted line. Okay, I'll turn that off under model menu. You'll also see my system is not chiral, but there's a little RS chirality, and if I turn that on, that will highlight chiral centers, and I'll point that out to you in a separate example. But that's also available. So I can turn off hydrogen bonding. There are a couple of other items here that are not necessarily applicable to looking at a single molecule, but I'll just reference them. Both global model and coupled are turned on by default. You'll see there's sort of a darker gray than the other items. Global model essentially means whatever model style I've selected, apply it to all of the members in my list. So if instead of looking at salicylic acid, if I had perhaps another entry in this list that was benzoic acid and another entry that was maybe para-aminobenzoic acid or something of that nature, I would, by global model being selected, all of those would be rendered in the ball and spoke style. If global models turned off, you can render them individually. Coupled behaves in a similar fashion. Coupled means if I've got a list file and I move my mouse to rotate or translate, that all of the mouse functions will be applicable to the entire list. So even though I may only be looking at one molecule, if I rotate it, I'm rotating essentially the axis point for all members of the list. And beyond that, labels is something that we can look at essentially for if we've done a calculation, we're looking at maybe charges, or we're looking at chemical shifts, or I can just label an atom by its elements. Ribbons are for biopolymers. We can do a rendering of a Ramachandran plot if we have a PDB file as well. I mentioned chirality. I didn't mention CFD, but I guess I can just click this to display it. CFD stands for chemical function descriptor, and CFDs are essentially the standard pharmacophore definition. So I've got essentially I've defined an aromatic here. I've got something that could be either a hydrogen bond donor or a hydrogen bond acceptor, and then over here I've got something that could be a hydrogen bond donor. So if I click on either of these and go to, for example, the properties dialog, which is under the display menu, properties, or it's the little sort of bubble icon with a little I for information, that will tell me, hey, I've got a CFD, and right now the carboxylic acid group is defined as a hydrogen bond acceptor or donor, or it could also be a negative ionizable. And these are customizable definitions, but essentially for anything that you build in Spartan, we'll use a set of standard defaults for chemical function descriptors. We use those in a calculation called similarity analysis, where we look at how similar one molecule is to another, or how similar one molecule is, or how likely it is to fit into a pharmacophore defined geometric position. So I can talk to that a bit later when we look at the calculation dialog, but that's something that I'm not planning to show today, but I can reference where that is in the manual if you want to look at that. Okay, so that sort of rounds out the model menu as far as visualization is concerned. Let me just pop back into, I'll close this file, and I'll pop back into the sketcher again to build a separate molecule, just to give a different illustration. I again chose benzene as a starting point, and again, it's the double click to insert the initial piece. To zoom in and out in 2D or 3D, one uses the center mouse wheel. You can't see what I'm doing, but I'm essentially putting my finger on the center mouse wheel and either moving up or moving down. That's true in 2D and 3D. I'll show you that in just a moment. With our initial molecule, I essentially was building, as you recall, by clicking and then dragging out and then releasing. Let me undo that and just point out one other build motif. If one wants to build via like ring merging, so if I grab this cyclopentane over here, I can simply double click on any point, and I can merge the ring essentially that way. So that's available. If I want to, for example, build indole, let's say over here I want to have a double bond instead of this single bond. With carbon selected, if I just click on this bond and then drag over here, I've now made a double bond. The same would be true for triple. So it's just a click, drag, and drop. And then if I wanted to make indole, again, maybe a substitution, so I need a nitrogen down here rather than a carbon. Substitution is just a double click. So anytime I want to replace an existing atom in 2D and also 3D in the organic builder, I'll show you, it's a double click operation. Okay, so I built indole and demonstrated ring merging. So I'll point to something I didn't do in my first example. You'll see at the very bottom of the menu, especially the bottom left-hand side, there are a set of 5 icons. The V or view rather mode is the glasses we talked about. This is the little undo arrow. There's essentially a level of undo. So if I didn't like my last substitution, I could undo that. This delete will do essentially what you would anticipate if I'm in delete mode and I wanted to delete a bond, or if I wanted to delete an atom position. It's a double click to delete. But let me undo that and let's draw that bond back. And the trash can icon is basically completely get rid of the structure I have on screen. So if I click that, I'm prompted with a little warning dialog. Are you sure you want to clear the current structure? Oh, I didn't mean to click that icon, so I'm going to say cancel. But the trash icon or clear icon is essentially will get rid of whatever you built on screen. And then the last icon that I really wanted to point to was this little broom is essentially a cleanup feature. So if I've drawn something with a ridiculously long bond or something that just looks a little odd, while 2D structures, there's not really much structural information to work with. We have essentially a 2D mechanics minimization routine that will sort of attempt to clean structures up. So if I click that, you may have noticed things cleaned up a little bit. I mean, size has changed and maybe some angles changed a little bit. I'll give you maybe a better example. If I had a long carbon bond out here and then I went to clean up, that would make that a proportion bond for a single carbon bond in this ring structure here. Okay, oops. But let me delete this. Okay, and then just back to indole, and I'll go back into 3D mode for this. Okay, one of the things that we talked about with regard to visualization in 3D was basically measuring distances, angles, and dihedrals. Let's take a look at some of the properties that are available as well. Rather than actually running a calculation at this point. I'm just going to retrieve this molecule indole from the database, so I'll have some data available. In order to access data in Spartan, at least most data, you'll need to have either retrieved the system from the database, the SSPD, which I'm going to do, or actually run a calculation. Otherwise, if I tried to look at a charge on this atom, there's no data. I basically just built it, so I don't know anything about it yet. But I'm going to retrieve indole, and I'm going to retrieve this from a density functional model. I'm choosing the Omega B97X-D model, and it's been calculated with a 631 G-star basis set. So I'm just going to say replace. And that just replaces the structure I had on screen with an entry from the database, so that if I go and look at the properties dialog, I'll be able to look at some calculated data. Okay, the properties dialog, we mentioned it earlier briefly, is accessed either from the display menu, so you can display the property, or its icon is this little bubble icon with a little eye for information. So clicking on that will bring up by default what we call the molecule properties dialog. So let me move my molecule over here to the left. Translate in Spartan, whether you're in 2D or 3D, is a right click. So with the right mouse button held down, moving the mouse to the right or left will translate in the X, moving it up or down will translate in the Y. And then, as I mentioned earlier, the zoom is accessed via the center mouse wheel, and that will translate in and out of plane or in the Z axis. Okay, so by default, properties will access the molecule properties dialog, and you'll notice that the molecule properties is a tabbed dialog. So right now we're under the molecule tab, but there's also a QSAR tab, a thermodynamic tab, a 2D drawing tab, which basically will carry around a 2D sketch of the system, and there's a 13C carbon NMR tab as well. I'm not going to go into too much detail about those just yet. I'll access those once we do a calculation in the latter part of the presentation. But I just want to point that this is, excuse me, this is a location where you would access calculated data once you've run a calculation, or as I did in this case, retrieved it from the calculations dialog, retrieved the system from the calculations dialog. So you'll see a couple of things: its name, its formula. Those are empirically generated. Its energy, this comes from calculation. Because it was a density functional model, the energies in Hartrees or atomic units. There's also an alternative energy, which is this T1 thermochemical recipe, and that will generate a heat of formation. You'll see immediately above that, there's also an entry for heat that is blank. Heat in the top row here refers to the NIST Chem Webbook database, and there are not too many, but there are a few thousand, maybe 3,500 or so experimental heats of formation that are available in the NIST National Institute of Standard and Technology database, their online Chem Webbook. And if that is available for your system, that will be pre-populated. So for most small molecules, you should see something. I'm actually surprised indole isn't in there, but for anything certainly a larger, maybe than molecular weight, 150 or 200, I wouldn't expect to see it. And certainly for anything novel that you build, it won't be there. But we do have a calculated heat of formation. This comes from the SSPD, but is also an available calculation in Spartan's calculations dialog. Also, for essentially any system that you run a QM calculation on, a quantum chemical calculation on, you'll have the energy of its highest occupied and lowest unoccupied molecular orbital. You'll also see in the calculations dialog, all of these guys, all of these entries are sort of preceded by a little post button. So that's an indication that, if you click on that, that will post the data that's there into the Spartan spreadsheet. There's a couple of other items. There's a dipole moment. This is calculated from quantum mechanics. There's a weight. This is essentially empirical based on weights defined for each atom type. The number of proton tautomers, there's a symmetry point group, a Cas number for the system if we happen to know it. We don't have every Cas number for every molecule that you would build, but for items that are accessed via the database, we probably have the Cas number for something like, I don't know, 55 to 60,000 molecules, and that's slowly being populated and rounded out for. Essentially, it will be there, I think, for everything in the database at some point. If there are any conformers, this guy is flat and rigid, so there are no conformers. But this would basically tell you the number of available or potential conformers if it was a flexible molecule. And then you'll see there's a different model referenced. This is actually what we believe to be the sort of minimum model and basis set size one can get away with for looking at energies of reactions. So if I wanted to define a chemical reaction, let's say A plus B goes to C, and I wanted to get reasonable data for that, whether it's endothermic or exothermic, and what the energy of reaction is, we recommend this omega B97XV model with a much larger basis set than the 631G star. So we've got triple zeta 6311 basis set, and then we've also extended that to 2DF and 2P. So it's a pretty large size basis set. So for anything that is included in the SSPD, we've also run a single energy calculation on that structure with this larger basis set. So that energy is available as well. So for the 305,000 structures or so that are in the database, and you can run this calculation for anything essentially that you build. There's a little checkbox for the dipole vector. So if I wanted to turn that on, it's a toggle. So you click it on and click it off. And if I maybe put this in a different rendering style, you can see the dipole a little bit better. Okay, so that's a sort of intro point to the properties dialog. So at this point, all we've really done is we built things essentially in 2D. We've converted them into 3D, and we've looked at maybe measuring some items, and we've looked at essentially the properties dialog as a place for accessing data. Let me now go to the 2D, or rather the 3D set of builders. So I'm going to close Indol, and I'm going to, rather than going to the file menu and going to new sketch or clicking the new sketch icon, I'm just going to go to new build, which was the traditional building motif in Spartan since its inception back in the late 80s to early 90s. We were one of the first companies to put a 3D graphical interface in front of computational chemists.
Dr. Sin, I just want to interrupt you. Dr. Sin, I just want to interrupt you.
I'm sorry?
Dr. Bala, any query you have till now? Hello?
Good, go ahead.
Okay, so
Okay.
it's just an introductory interface. We are now going to deep section. Please continue, sir.
Go ahead.
Okay. So in moving into the 3D building, we'll click on new build, and this will open off to the right-hand side of the interface a set of essentially a tabbed or buttoned model kit. And you'll see there's the organic, the inorganic, peptide and nucleotide builder, the substituent builder that I mentioned earlier. And this ChemDraw builder is actually not turned on by default, but that can be turned on via the preferences dialog, and I'll show you where that is in the future. If you have a current version of ChemDraw on your computer, and if your computer is a Windows machine, you'll be able to access ChemDraw from within Spartan. We don't have the ability to do that on the Mac or under Linux, but we can open ChemDraw files with the Mac and Linux versions. There's just not this linkage within the program. It uses a Windows technology to do that. So the organic builder is organized essentially hierarchically. We've got a set of carbons, nitrogens. You move to through the periodic table, and then we've got a set of essentially bonding types or configuration types. So I've got an sp3 carbon, an sp2 carbon, an sp carbon, etc. Building in 2D or as we showed earlier, is essentially follows our 3D mode. So if I want to begin a structure, let's say with an sp3 carbon, it's just a double click as the initial entry point, and you'll see I've got a tetrahedral carbon up here, and I've got essentially the 4 open valences. Those are highlighted in yellow, and so if I want to add to this with my sp3 carbon still highlighted, essentially just clicking on a yellow open valence will add. So from methane to pentane, if I wanted to make this pentanol, let me just choose I mentioned earlier double clicking as a substitution model. So let me point out if, for example, this third carbon, if I wanted this to essentially move to an sp2 carbon, maybe I wanted to put a carbonyl group there. If I double click on that, that will convert it to this alternate sp2 from sp3. But note that because I've got 2 bonds here, a legal substitution really wouldn't be to go to an sp carbon. So if I try and do that, the organic builder has sort of a built-in I guess construction checker. It only allows you to follow the standard rules of valence. In the inorganic builder, you can essentially do any customization that you want, or any substitution that you want. The inorganic builder sort of assumes that you're a bit more expert of a builder and you know what you're doing, but the organic builder prevents you from doing anything essentially non-standard or perhaps nonsensical. Okay, so you'll see that these are all rendered right now in the build mode as yellow open valences. But if I go to the view mode, which is again the glasses icon, it's also available under the build menu view mode. Spartan will automatically fill all those open valences with hydrogens, so you don't need to do that. So we took a quick look at the organic builder. Let me point to a couple of other pieces in the organic builder as well. I'm going to close this existing file and we'll open a new file. We just looked at essentially this palette here. What I didn't click on are the set of groups. So they're a set of functional groups, and they start out with alkenyl, alkynyl, alenal, down to carbonyl, nitro. So just a handful of groups. We try and keep the menu items not too extensive so that they'll essentially fit on screen. But standard functional groups are here. You'll note that some of them I've chosen carboxylic acid, but you see it says carboxylic acid / ester, and that just depends on the attachment point. So once I've selected a group in the upper portion of the model kit, there'll be a 2D rendering of that. And then if you see a little yellow dot, like a yellow open valence position, this is basically saying, where am I going to attach? So if I had a sp3 carbon here, and then went back to that carboxylic acid group, if I add here, I'm making acetic acid. If I undo that and add here with the ester attachment, now I'm making methyl formate. Also in the organic builder, there are a set of rings, a bit more than the 2D builder. These are all carbon-based, so hydrocarbon rings. So there's a small palette of these. This can be actually augmented either via substitution, or there's a set of alternate rings that are accessible under a drop-down menu called More. But basically, any of the standard hydrocarbon rings will be available here. So if I wanted to put a cyclopropane functionality over here. So groups, rings, More points actually to the file menu. So if I click on More at this point, it's pointing to a location out in the installation folder of Spartan, and it does that by default. And there are just a set of libraries that one could access. So if I wanted saturated nitrogen rings, for example, I could say open that, and now my more essentially points to a set of saturated nitrogens. Okay. Okay, so that the clipboard is basically if you do a copy function, so either edit menu copy or right click copy or control C. Anything that's on screen, let me use this as an example. If I do control C or right click copy and then click clipboard, that actually puts what I have on screen over here as a building component as well. And you'll see if you do that, there's also essentially an attachment point defined. So if I wanted to use this as a building model, I need to choose an appropriate attachment point. Let's say I wanted to attach over here. So you can kind of use the clipboard to bootstrap if you want, like if you wanted to build a polymer, essentially, you could do that. You know, build your monomer, make a copy of that, build a dimer, make a copy of that, and then you could, you know, go from dimer to tetramer, etc. So the builder is pretty convenient there. And then at the very bottom of the builder, you'll see there are a set of smiles inputs or Inchy inputs, and these are basically you need to copy paste or type those in. Same for smiles. And at the bottom, these are common building functionalities. So there's a delete, make bond, break bond, or minimize. So if I wanted to make a bond, let's say between these adjacent carbons here, it's just select one open valence, select a second open valence, and that will make this bond convert it from a single bond to a double bond. The minimize function essentially applies the Merck force field to clean the structure up. So it will reduce strain on the system. So if you build something where you've got crowding, sterics are involved, or you've got something that's in an unfavorable rotamer position, the minimize will essentially arrive at the closest local minima to what you have, but it will reduce strain on the system. And all of these building icons that are appearing permanently on the bottom of the builder here are also available under the build menu. Okay, so that covers essentially the organic builder. Let me quickly pop into the inorganic builder for you. So we'll go to new build inorganic, and this essentially encompasses the rest of the periodic table. So let's say I wanted to, for example, build let's build chromium tricarbonyl, for example. I want to start out with you think I'd want to start out with a benzene ring, but I actually want to start out with a coordinated benzene ring, a ligand with a bond point that's essentially at the center of the ring. So I can go to the ligands menu and choose benzene. The initial build is a double click. So here's benzene coordinated with a bond to the center of the aromatic ring. And then I want to now go to select from the periodic table chromium. So essentially this bar right here underneath is essentially a selection bar. So whatever has focus, if I click on that, that will give me options to choose from. So I've got an atom selected here, so I can now choose from among the periodic table of elements. So let me go to, excuse me a sec, to chromium. And then I need to choose a coordination in the inorganic builder. Let me choose tetrahedral and build here. And so now I've added a chromium to the benzene ligand. And then I'll now go under the ligands menu again. And in this case, I'll choose carbon monoxide. So I can build 1, 2, 3. I'm just clicking on the yellow open valences, and I can build chromium tricarbonyl. Let me click the minimize button to clean the structure up a little. Actually, and you'll see it happens to be in the Spartan molecular database, so it exists here as well, and its name will appear. Or whatever you wanted to build in the inorganic builder. Essentially, the rules of valence are are not followed. So if I wanted to build something that maybe doesn't make a lot of sense, I just point that there are some pitfalls. If I chose, for example, an octahedral configuration, all right, well, that doesn't really make sense for carbon, right? But if I double click, look, now I've got an octahedral carbon. So you have the ability to play some games that are essentially not standard for the periodic table, and any click is a legal substitution as well. So if I wanted a boron here, I could do that. And you can use this in conjunction with, oops, edit undo. You can use this in conjunction with the builder palettes down here or tools to make sense of your system. So if you build something that's nonsensical, you can certainly avoid that pitfall by using the building tools at the bottom. There's also in the inorganic builder, there's a set of bonds defined here, and you have the ability to essentially define bond type. So let's say, for example, if I put well, let's get rid of this guy. Let me do. I'm gonna choose carbon, double click, and I'll choose tetrahedral, double click. What I'll do is I'll round this out by grabbing hydrogen, and I'll add hydrogen to the 3 open valences, and then I'll demonstrate a tool that's useful in the inorganic builder as well. If I want to get another hydrogen here, but I've got no open valences available, how do I do that? Well, I've chosen hydrogen, and we know that double clicking is how we start building. So if I just double click on the background, I'll insert a hydrogen. So now I have a separate non-bonded hydrogen here. And if I want to make a bond here, I'll simply click the make bond icon. And I have one open valence defined, but I don't have another. So in order to bond to this center atom, it's just a double click. So anytime you want to bond to something that doesn't have an open valence available, if you double click on it, that will complete the bond. I wanted to just display across the bottom the bonding types. So this is single selected, but if I wanted to choose aromatic or double and make a substitution, double clicking will essentially do a replacement. Like we talked about, double clicking in the 2D builder, also in the 3D builder, works for atoms and for bonds. Okay, so that's the inorganic builder. I'll just quickly point to the peptide and nucleotide builders. I'm not going to spend a lot of time here. I just want to introduce them. So if you can either build via sequence or essentially look at the individual residues. So if I choose glycine or alanine, you'll see its rendering will appear in 2D. If I choose sequence and the same thing, glycine, and now the next time I click, I will have made a glycine alanine, essentially a dipeptide. Building is accomplished. The initial step is just a double click. And with regard to the peptide builder, there's a terminate function, so we can either terminate as neutral or as the Zwitter ions. If I don't terminate, those open valences at the end will just be filled with hydrogens. There's we were in a alpha helix mode, so if I was to, under the model menu, turn on ribbon, I'll see I've got a helical backbone essentially started. You can choose the sheet as well if you're building in sequence. Other basically will allow you to customize the 5-side dihedral angles. Okay, so that's the peptide builder. Nucleotide builder, it behaves in a similar fashion. There's double-stranded, single-stranded DNA, double-stranded, single-stranded RNA, or the DNA RNA or RNA DNA hybrids. If I have the sequence checked, then I can build up a small piece of DNA. and I was under single-stranded DNA, so I don't have its partner. If I switch to double-stranded DNA, and I'll do edit menu clear, and now do a double click. Now I've got the double-stranded background. Okay, you can configure the ribbon if you are interested in looking at things like, now I wanted to configure the ribbon by its strand, so that I'm looking, defining one as red and one as blue, or if I wanted to look at it by residue, that's all doable. So there's a lot of customization that's available. If in this case, if I wanted to maybe put this in a tube rendering and look at the hydrogen bonds at the same time, I can look at, where do I have CG linkages or AT linkages, and so where do I have my double or triple bonds between the strands, etc. Okay, so organic, inorganic, peptide, nucleotide. Let me just quickly point to the substituent builder. I referenced that earlier. If I go into the organic build firstly, and let me choose maybe let's get naphthalene. Maybe we build quinoline. I'll do an aromatic nitrogen over here and double click. So to just get a quinoline scaffold, and then go into the substituent builder, you'll see I've got a set of R groups, and those range from methyl down to isobutyl, T-butyl, etc. To aromatics, a set of common aromatic rings. I've got OR functionalities, so methoxy, ethoxy, and propoxy, etc. Electron donating, withdrawing, or leaving groups. And then I also have a set of custom groups I can define myself. But let's just say for the time being, I wanted to put, at this position, a set of R groups, and maybe at this position, a set of electron donating groups. Essentially, what I can do is, by clicking this generate list, I can propagate this scaffold and generate. It's going to say, hey, how do you want to, it's going to give you a new template. How do you want to name it? Do you want it in the current document or a new document? But when I click generate, you'll see that essentially at those two positions, Spartan is adding essentially everything that we've built. So the first molecule in this list would be my scaffold with these definitions. But then you'll see in the lower right, it says I've got 82 molecules, and these consist of that, essentially all possible substitutions. We haven't done anything with the structure yet, so we need to minimize that if we wanted to clean it up. But if you wanted to build a virtual library of substituted systems with a common moiety or a common scaffold, you'd use the substituent builder. Okay, so that covers organic, inorganic, peptide, nucleotide, substituent. I'll just quickly show you the ChemDraw builder and how that operates, assuming I have it installed. I think I have it installed on this machine. Unfortunately, let me. I'm only sharing my my Spartan window right now. Give me just a second, and I think I can use the screen sharing tools to share ChemDraw. Okay, so I've got ChemDraw on screen now, and I'm not an expert at ChemDraw, but let's build something in ChemDraw. Maybe something with a little character. All right, just something. So I've got a little something not quite so boring. Okay, once I've built this in ChemDraw, all I do is I close ChemDraw. And now that I've closed, I got to go back to the screen sharing. Give me a second, and I'll share my Spartan screen again. Hadn't anticipated that. Sorry about that. You'll see that you built it in ChemDraw. The little rendering of your ChemDraw file is here in 2D, and the ChemDraw structure has been converted to 3D at the top of the builder, and then you just double-click in the interface in order to pull that into 3D. And then view mode will fill up those open positions with hydrogen. So We have our own 2D builder that we use more commonly now, but previously customers had asked, can we use ChemDraw to build? You can grab the ChemDraw interface from within Spartan if you have the Windows version. Otherwise, you just need to build it in ChemDraw, for example, on a Mac, and then just save the file, and you can open that in Spartan. And I'll point quickly to the other input model. So we've talked a lot about building, but if I just go to the file menu and then open, or it's this little open folder icon, I'm porting to a folder on my computer that I have a bunch of molecules in. By default, Spartan documents are highlighted, but if I switch that to all available files, let me sort this by type. So there's a bunch of Spartan folders at the top. Get a little bit further down. But you'll see there's some crystal input files, some .cif files we can read. There's some CML, chemical markup language files, ChemDraw files. These DX files are infrared database files. There's an INCHI string, some CSV files, mol and mol2. All of these are files that that Spartan will be able to read. So if I just if I go back up to where I had some sample ChemDraw files, click on one of those. So if I open the ChemDraw natively, it will open in Spartan's 2D build, and then if I click on the view mode, that will pull it into 3D. Okay, so the three main ways of accessing molecular structure: build in 2D, build in 3D with a set of tabbed model kits, or the file menu. Okay, let's go to let's run a calculation at this point. So I'm just going to build something quickly in 3D. Let me build. Let's see. Let me build para-aminobenzoic acid. So I chose a sp3 nitrogen. Double-clicked on an open valence here. Under the group menu, I'll choose carboxylic acid. It looks like the ester functionality is referenced, so I'll move that to connecting at the carbon and put that in the para position. Okay, so para-aminobenzoic acid. I can either retrieve the structure from the database if I want data, or I can run a calculation. So let me point to the setup menu and the calculations dialog as the sort of organizing tool for setting up calculations. Either the setup menu calculations dialog here, or its icon is also always sort of shown on screen. It's the sort of icon that looks like a window with a little gear on it, and that is the calculations dialog. Okay, so the calculations dialog refers to essentially this is a one guy list, or a document with one member in it, just the PABA molecule. But had I gone file menu and then build new molecule instead of new build and put a second molecule in the file, this global calculations would be something to pay attention to. It's on by default, which means what I set up in the calculations dialog, I'm going to run that calculation for every member of the list. If, for example, I wanted a different type of calculation for one member of the list, I would need to turn this off and then re-enter the calculations dialog when I had that special member of the list access to say, hey, this guy I actually want to run a different calculation. Maybe it's because it's got a charge and I don't want to say that everything is neutral, or maybe I want to use a bigger basis set for this particular model in the list. But by default, calculations will be in a global mode. So when I run the calculation, it will apply to every member of the list. Okay, the calculations dialog is also set up fairly hierarchically. So under the calculate section, we have a set of tasks, and those range from energy, which is basically give me the energy of the molecule as it's drawn on screen. Equilibrium geometry, which says take the molecule on screen and iteratively do a geometry optimization where you solve for the structure and you modify essentially angles and distances and dihedral angles, constantly pushing energy in a downward direction until we get to a flat space on the potential energy, essentially for pushing potential energy down until we get to a flat space in multi-dimensions where we found a local minima. Equilibrium geometry does not guarantee that you will find the global minima. It just means that you'll find the closest energy minima for your structure. Transition state geometry, which is essentially the opposite of what I just said. We're looking for a minima in one dimension, but essentially we're at a maxima in essentially all the other dimensions. We're looking for a flat space at the top of a hill that references a transition state. Equilibrium conformer will find the best conformation for the system that you've drawn based on the model that you choose. Conformer distribution will do the same. It will run that conformational analysis, but instead of returning the best conformer only, it will return the best conformer and the set of associated conformers that contribute to the Boltzmann distribution based on a rule set. So I think we keep, I want to say it's like the lowest energy, and then within 40 kilojoules, we keep the other conformers that reference. And I think there's a maximum of 500 unless you want to keep more than that, which we can do. Energy profile is essentially coordinate driving. So if I wanted to force a reaction by decreasing the distance between two atoms, or if I wanted to rotate around a dihedral angle, for example, and look at energetics, I could run an energy profile calculation. NMR spectrum calculation is a special task that does both conformational searching and NMR chemical shift calculation as well, which will essentially take into account Boltzmann weight. So you can think of the NMR spectrum task as a Boltzmann averaged spectrum. And then the bottom two are similarity library and similarity analysis. Those both refer to utilizing that chemical function descriptor that we talked about earlier. So those are the sets of tasks. We're going to choose equilibrium geometry. At ground state, there are essentially two entries here. You can go beyond first excited. It's a type in if you were to go to the options menu and say I wanted, I could do second excited state. I wrote E state equals. There's a whole set of keywords that are documented that are available as well, but the majority of things are done at ground state. Spartan will run calculations in gas phase by default, so essentially in vacuum. There are a set of sort of standard solvent models that are available, and then there's a whole host of, I don't know, maybe 150 to 160 other solvent models that you can choose from as well. But if you choose water, for example, let me just point to this so you see. Okay, the calculations performed in the presence of water with a dielectric constant of 78. If we choose, a polar solvent, I want to say, trying to remember what we use. I think what do we use? Tetrahydrofuran. I can't remember. Oh, dimethylformamate. So there are a set of standard solvent models that we use, and we use the CPCM, which is a variation on the polarized continuum model. But Spartan also includes SM8, SM12, SMD, so some of the true R solvent models are available as well. But by default, we use a continuized polarization model. So let me put it back to gas phase. With underneath here, you'll see calculate, and then with will choose essentially the theory level that you're going to use. The default is density functional, but there's molecular mechanics, semi-empirical, Hartrud-Fock, DFT, and molar plus set are available for equilibrium geometry. If we were just in the energy calculation mode, that also opens up some additional wave function based correlated models. So a couple cluster things would be available here, and some thermochemical recipes. Earlier I mentioned the T1 thermochemical recipe for calculating heats of formation. there's also the GX model. So there's G2, G3, G4, G3, and P2. So the Gaussian variants on thermochemical recipes are also available. Okay, so let's go back to, in the interest of doing something very quick, as far as not wasting a lot of our time, I'm just going to do a very simple semi-empirical calculation. And I'll also tack on an infrared spectra calculation. This will be very fast. Typically, the options field down here is not highlighted, so I'll just turn that back off, and this would be kind of the default. Off to the right-hand side, you'll see one other piece of input that's required for your calculation: the total charge and the number of unpaired electrons. By default, this will always be set at neutral and 0. But if I had a cation or an anion, if I had something with a multiplicity, I would need to note that here. So if I had a radical, it would be, one unpaired electron. We would say it's got a multiplicity of 2, or we would call it a doublet. But then I would go in and make a change to this. But this will cover the majority of, standard organic systems. We should be neutral and 0 unpaired electrons. I'm simply going to click the submit button down here in the lower right corner. Submit is also available from the setup menu, but if I click submit, Spartan will say, hey, what do you want to name this guy, and where do you want to save it? So I'm going to give it its default name. Looks like I've already got an example in here, so it's calling it _1. Before I click submit, I just want to point out one other piece of the Spartan parallel suite. With the parallel suite, you have the ability to have your license act as a computational server. So this says it's going to submit locally, but if I wanted to, there are a number of other machines that my box is configured to see. One of them is in the cloud, but I could remotely submit the calculation off of my machine. So I'm not using my local resources, but for example, this machine called White in my office is a new Linux box I got a couple of weeks ago. So if I wanted to submit to that, I could submit to that. And that's like an 8-core Linux box. It's faster than my desktop machine, and it has a Spartan Parallel Suite license. So if you opt for the Parallel Suite license and you put that on a higher functioning server, you could use that as sort of a computational device. Or if you had a cluster available, you could use that as your computational device, and you could remotely submit to that. I'm just going to run the job locally. I'm going to say save, and the job will start. This will probably finish before I have time to demonstrate this, but if you go to the options menu, there's a monitor. Actually, I grabbed it. That will, the job's finished now, sorry. The monitor will allow you to see what's going on with calculations. I'll run a job that will take a little bit longer in a moment, so you can sort of see the number crunching as it's going on in the background, but this job completed already. Okay, so with this completed file, and I apologize, we're going to go a little bit over, obviously, the intended time. So let me say that we'll go for another 15 or so minutes, and then you tell me if that's okay if we need to stop. But I ran a little bit over on the building portion. But what I want to show, once you've run a quantum chemical calculation, and it essentially doesn't matter what theory level you've chosen, you have the wave function, and from that, you can look at things like, when we were in the properties dialog, we could look at the orbitals. So the energy of the highest occupied molecular orbital or the lowest unoccupied molecular orbital. Spartan also has the ability to look at multiple orbitals. So let's look at the output for this job. Let's go either under the display menu and choose output, or it's a little blank page icon. It's just to the right of the calculations dialog. The output is organized hierarchically. There is a summary. There is text output. There is verbose output, which in this particular case is not relevant because verbose output refers to the QChem output, and the job I chose was semi-empirical. That's not a QChem model. That's something that is available just from Spartan. So this will just give you a standard text output for verbose. molecular reference, if for example, I'd retrieved this from the protein data bank as a starting point, or the Cambridge Structural Database, which is another database that Spartan can interface, there'll be the reference available, and a job log. And the job log is really more sort of a troubleshooting tool, if you like, but it basically will point to all of the different executables that fire up and run when a job is submitted to the background. So we tend to think of Spartan as a single program, and certainly the interface is a single executable, but there's a start executable that fires up when you submit a job. The initial thing that's done is a mechanics optimization, so molecular mechanics. There's an executable that runs. I chose a semi-empirical job, so it's accessing a semi-empirical executable. There's a property executable that runs to calculate properties at the end. And then there's a final pruning step that runs the job that packs things up and then releases those as a single output. So just with a single job that was submitted, and a simple one, we actually accessed 5 different back-end calculations. So let's go back to the summary. I did happen to click the Raman table, the IR box. IR and Raman frequencies are identical. They're obviously not the same as far as intensities are concerned, but because I chose that, if I click this little drop-down triangle, you'll see that will populate with the set of uncorrected frequencies and intensities. And I did a semi-empirical model, so this won't be terribly accurate, but it was calculated. Because I did IR as well, there are thermodynamic properties, so I can get things like 0-point energy, enthalpy, entropy, Gibbs energy, etc. Those all come from the vibrational analysis that's part of the IR calculation. Molecular orbital energies is what I mentioned earlier, so not just the HOMO and LUMO, but the LUMO +1, the LUMO +2, and I think the first 10 or so, so the HOMO and the next 9. And this says it'll show the first. If you want more, you can get at more. This is all just tabular data. It can be exported to Excel if you like, or printed. Atomic charges. So this will run through 3 charge models that are available for within Spartan. So there's natural charges, Mulliken charges, and electrostatic charges. And I'll show you another place that those are available. Calculated bond orders. Okay, so there was a Mulliken analysis. We do Loudon analysis as well for Hartree-Fock and higher models, but the semi-empirical is only implemented for Mulliken bond orders. Okay, so that's a sort of a output summary. Text-based or sort of older school way of looking at kind of an ASCII printout will show you the bit of the details of the job. Hey, it was a PM3 calculation. It looks like my system had 27 shells, 17 were S, 10 were P. Hey, I said it was a neutral. I said it was a 0 unpaired electrons, which gives it a multiplicity of 1. It started out, it calculated its initial Hessian with molecular mechanics, and then it looks like it worked through 7 optimization cycles before we found that local minimum, before we found the flat space on the potential energy surface. The total final calculated energy was -289 kilojoules per mole. Semi-empirical models will give you energy and heats of formation. I also did a infrared calculation, and that completed, and then it essentially will give you, hey, the total job took this amount of time. With regard to the charges that we looked at a moment ago, let me just point out, so far we've seen the properties dialog associated with the structure. I can show you some other panels now that I've actually run a calculation. I didn't check the QSAR box, so some of this stuff didn't populate, but area and volume and polar surface area are calculated. Ovality is calculated. Because we did an infrared calculation, the thermodynamics is populated. So I've got heat capacity, and then as I mentioned earlier, 0-point energy. I've got enthalpy, entropy, and Gibbs energy. And I think that's all that we can really hit right now. We can look at the 2D drawing, but I didn't do NMR. NMR is not available for semi-empirical models. It's available for Hartree-Fock and density functional. And for practical purposes, it's really only useful for density functional models. The Hartree-Fock models are not sufficiently accurate to give good qualitative data for NMR. So we looked at properties of the molecule, but actually, sorry, let me pull that back up. What happens if I actually click on an atom? All right, well, now I'm looking at the properties of that atom. So the charges will be available, and in this case, that's about all, since I didn't do chemical shifts. But electrostatic, Mulliken, and natural charges. Had I chosen to freeze an atom, and I'll talk about that in just a moment, you can run calculations with some artificial constraints put in place. I could constrain a distance angular dihedral, or I can freeze an atom or a heavier or hydrogen atom position and hold that fixed during the optimization process. But I didn't do that for anything in this case. So properties refers essentially to the property of whatever you've clicked on. So if I was to click on this double bond, hey, it actually will tell me something about the bond properties. Or if I click on the nitrogen down here, it will tell me the properties of this nitrogen. So, and again, anytime you see the this little post icon, that means that data is available to post into the spreadsheet. So if I wanted to post the electrostatic charge for this nitrogen, I could post that into the spreadsheet. Okay, in the output summary, one of the little triangles I clicked on was the molecular orbitals. Let me show you graphically a way to look at molecular orbitals. So either under the display menu and clicking on orbital energies, or it's this little orbital sort of diagram to the right of properties. If I click on that, you'll see on the left-hand side of the screen, you get a little orbital energy diagram. And we basically take the HOMO and the LUMO and then a range. You can change the range, but for practical purposes, we limit the number of orbitals that we pre-calculate, I think, to no more than 10 orbitals. You can request the graphical calculation of any orbital that you want, but as far as the orbital energy diagram is concerned, there's some constraints that we put in for sanity checking. So if I wanted to look at, hey, what's the energy of the lowest unoccupied molecular orbital? I can do that. I'm just clicking on the entry in the orbital energy diagram. Same thing with the highest occupied molecular orbital. So you see it's distributed, delocalized over the aromatic ring, above and below, a little bit above and below this carbonyl oxygen. You'll see in the lower right corner, like I mentioned earlier when we were measuring distances and angles and et cetera, there's some information available. In this case, the actual energy is here. If I click on the post button, it'll post that to the spreadsheet. There's also a little drop-down menu for style. By default, these orbital energy diagrams are done, I think, at a medium resolution with a solid style, but you can put that in a mesh rendering or a transparent rendering if you like, as you can sort of see underneath the surface. Okay, so that covers a quick way to get at molecular orbitals, and these actually get essentially the graphical models get calculated on the fly anytime we have the wave function. So if you run a QM model or if you've retrieved a structure from the database, you'll be able to generate the orbital energy diagram, or you'll be able to access graphical models. So the next thing I want to point to once we've run a QM calculation is that we can look at some graphical surfaces. We can do that by going to the display menu surfaces, or it's actually the electrostatic potential map icon for benzene is what that is. But if I click on that icon, that will pull up a little dialog for me. And you'll see in the bottom left of the dialog, there's an add button. To the right of that, there's more surfaces. You can kind of think of the add button as the standard graphical models that we use in Spartan, and then more will allow you to do some additional customization. So let's just add a few surfaces. We looked at the HOMO and LUMO already, but maybe I'll add the LUMO just because I'll also add, I'll show you the LUMO map. Let me add density, which is the electron density. I'll look at the electrostatic potential map, and we'll add the LUMO map. You see at the bottom, there's also an entry for more surfaces. So both that and this button do the same thing. But for the 4 surfaces that I've chosen to calculate, excuse me, I'm going to sip my tea. We'll see those are now available. And my setting was, my resolution was set at high, which is just a prettier picture. It's basically more triangles are used to generate the surface. Let's look at the density. So the second entry down, density. This is the electron density. And if I go further than saying it's the electron density, if I pull up the properties dialog and click on the actual surface, you'll see I'm now looking at the properties of that particular surface. So it says it's an ISO value of 0.002. Well, what does that mean? That's essentially 0.002 electrons per cubic bore. So it's basically capturing all of the electrons, a surface associated with almost all the electrons in the system. So it's a 99.18% enclosure as far as the electrons are concerned. So if I switch from the style of solid to mesh and show you what that means sort of in practical terms, or maybe transparent, if I compare this to not a ball and spoke model, but a space filling model, you'll see they're very similar. There's interpenetration above and below. The space filling model is essentially rendered based on crystal packing data, so standard CPK definitions for the atomic radii used, and the electron density essentially maps very closely with that. So we chose that value, and we basically chose it once, and that's the default. That does not mean that you can't look at other ISO values, and in some cases it's quite useful to do that. For example, if I'm essentially looking at the electron density surface, which answers the question, how close can I get to the system before I'm going to feel some steric pushback? So it defines the atom positions basically. But if I wanted to look at the electron density associated with the bonds, instead of a surface of 0.002, I could change that to maybe 0.08 or 0.07. And you'll see that, hey, look, now I've got a little hole in the middle. But in addition to that, I'm essentially tracking or looking at the electron density associated with the bonding. And if I hide the model altogether, you'll see essentially this is defining the ring system, and then the carbonyl functionality above, and the amino function down here below. And there's actually, under more surfaces, there's a density bond, and I think this 0.08 value is actually what we've identified as defining that. You can, you can play your own games there, and that will change the rendering. But in any event, so there's some customization with regard to the surfaces as well. Let me go back, turn on ball and spoke. Okay, and I'll close out of this. I'm going to leave well, let me turn density off for just a moment, and let's go back and look at the LUMO, the lowest unoccupied orbital. Basically, if I'm going to react with this guy, I've got electrons available. If I'm a nucleophile, I've got some extra electrons. Where might I be interested in doing chemistry? Well, I'm going to put those in an unoccupied orbital, and I'll want to put them at the lowest energy one, most cases, because that would be energetically favored. So these are areas where there might be some interest in a nucleophile attacking. And if I put that on screen at the same time, I can sort of see this in conjunction with the density map. Maybe I make the density map a little bit smaller than 0.002. Oh, let's say 0.00. Now maybe. At a certain point, I'll get low enough where there'll be interpenetration between the orbitals and the density surface. Or another way to do that is, rather than looking at the density in conjunction with the LUMO map, is to actually map the value of the LUMO on top of the density structure. I didn't pick a terribly good example in this case, but let me go back to the properties dialog, and I've just toggled the range. There was a default range associated with the map, and then there's a max min range, and I'll see a couple of spots that are potentially interesting for a nucleophile as far as an attacking location would be concerned. So the LUMO map is one of the graphical models that we use in Spartan that can help identify locations of potential nucleophilicity. We looked at the density before. Let me add one more surface that I'll need to pull from the more surfaces, and that is the surface of potential, which is essentially the electrostatic potential. The electrostatic potential is a funny kind of surface. It basically says if I was to take a point positive charge out here somewhere far away from my molecule, and then approach my molecule and ask the question, do I feel attracted or do I feel repelled? And what level of attraction do I feel? So if I'm a point positive charge out here and I approach this molecule, I'm going to be attracted in a couple of obvious locations. The lone pair around this amino group here, the two lone pairs that surround the carbonyl oxygen, and the lone pair rather that the two lone pairs rather that surround the hydroxy oxygen as well. So this is areas that I'd feel attracted, well, because there's electrons there. And if I look at that in conjunction with the electron density and ask the question, well, where can I touch? I can touch the surface. And then where am I attracted? Well, I'm attracted here and here. In the same vein that we looked at the LUMO map, we could look at what's called the electrostatic potential map and get that same rendering. So I'm attracted to carbonyl oxygen over here. I'm attracted to the hydroxy oxygen here, and then also the lone pairs that are accessible at the top part of where the let me make it transparent so you can see through it. At the backside, I guess, of the amine group, where away from the protons. And the electrostatic potential map is used as a graphical indicator for electrophilicity. So there are a number of standard graphical models that Spartan uses that are available once you've run a QM calculation and or retrieved a system from the database. Okay, so kind of cover surfaces. Let me we looked at the orbital energy diagram. Let me also go to we ran an IR calculation. We just used some empirical, so it's not terribly accurate, but let's use it just as an example to display the spectra. Either from the display menu, spectra, or the spectra icon is immediately to the right of the surfaces icon. That will pull up a spectra pane, and in the top left corner of the spectra pane, there's a little green plus icon that references add. If you click on that, you're given basically a little menu of choices. Anything that's grayed out just means that I don't have data for it. So the left-hand column is calculated. The right-hand column is experimental. Experimental is grabbing data from the NIST website in the case of UV-Vis or IR, possibly Raman. I'm actually not sure about that one. The experimental data is grabbing the NMR shift database that's hosted out of the University of Cologne for proton and carbon NMR. But we did a calculation of infrared, and this is available. We'll give you a little IR plot. This can be printed if you like. There's a little probe down here. If I move, I clicked on it to select it. If I move over a peak, you'll see there's a little yellow line here that's associated with that, and that will say I have highlighted this peak, and I've just clicked on the carbonyl stretch in this NMR spectrum. It's off. It should be lower, but again, we use the semi-empirical model, so don't base your impression on the results for this model. I can retrieve this from when I do that, I'll retrieve this from the Spartan spectrum properties database, and now you'll see a different spectra plot, and we would expect that the carbonyl shift should be a bit more accurate here. Oops, where are we? There we are. All right, so something on the order of 1700 or so. If I actually go on the left-hand side of the plot, there's a little table icon. If I click on that, that will actually pull up the calculated frequencies and intensities, and you'll see the box I've selected is, what does that say, 1752. So sort of spot on for the a carbonyl moiety as far as vibrational analysis is concerned. The spectra pane will access calculated and experimental spectra for IR, for Raman, for NMR, proton and carbon, and then for UV-Vis as well. What I'll do, rather than running an NMR calculation, since I've retrieved this guy from the SSPD, which has calculated NMR included, I'll go in and pull up a display of the NMR as well. That will actually just add another tab to the spectra pane. So if I go in and choose, hey, I want the calculated carbon shifts for this particular PAVA molecule. If I click on my little probe and then move that over, you'll see that I'll highlight the carbons associated, or if I believe if I tap on a carbon, I'll highlight the shift associated with it. There's a default range. It's 0 to 150 ppm. Similar functionalities like we use to move the molecule out here, if I hold the right mouse down and move right and left to translate, that actually applies to my plot. If I hold the right mouse down, I can rotate, or not rotate, sorry, I can translate right and left. So there was one set of carbon shifts that were off the range, that were higher than 150, but I can access it. It's the carbonyl actually. The tables are also available here if I'd run or if I had experimental data as well. And actually, let me see if I grab that. I would assume that this is available. Yeah, so I downloaded the experimental data as well from the NMR shift database. I did that by going to the add, and then I clicked 13C experimental, and you'll see that a blue line now appears here. So the red line is calculated, the blue line is experimental. And you'll see we're pretty good. So here's my my calculated, and here's my experimental. Okay. So let me close out of the spectra pane and just point to one other location where the spectra data would be available if you'd run the calculation. If you go to the molecule properties dialog and then actually click on the atom or an atom, you'll see that the shifts will be populated. So in this case, the calculated shift was 164.7. The experimental was 169.1. So we're not far off. With EDF2, which is the density functional model that I chose, I retrieved from, is actually not as accurate as this other model, the Omega B97XD. Spartan has run through 4 different iterations of analysis as far as NMR spectra are concerned. The first thing we did when we had this ability to calculate shifts from the QChem package was do a big, large assessment. And it turns out that, you know, raw, unaided chemical shifts, at least for carbon, are on the error of plus or minus maybe 4 to 5 ppm. So not terribly useful as far as an aid in assignments are concerned. But what we've done now, and we're on our 3rd generation of empirical correction schemes, is we've got a system in place that takes into account the certainly the calculated shift, but also the knowledge of its neighbors. And so we've got a big parameter scheme based on, you know, having, I don't know, I can give you details, but thousands of, you know, sp2 carbons at an adjacent position, or sp3 carbons at an adjacent position. And there may be something on the order of maybe 23 or 24 parameters in this correction scheme, but we've narrowed down the errors from almost 5 ppm to something on the order of, you know, maybe 1.5 to 1.7 ppm for carbon, and it's very small for protons, something like 0.1. So the quality of calculated shifts from Spartan at this point, with that Omega B97XD model and also from the B3LYP model, are definitely sufficient to be a real assist in assessment of an assignment of NMR. And further, I'll add, with the Spartan 18 version, when we looked at the calculations dialog, there's a checkbox for NMR, so you can certainly calculate NMR anytime you see that that's available. But this particular task, let's see. Well, if I go to the NMR spectrum task, that's the one that I mentioned does the conformational analysis in conjunction with the NMR spectrum. So if you look down here, we've sort of hidden it because it gets rather confusing, the actual recipe. But what we actually do, if you look at the details, is we start out, we do a conformational search with molecular mechanics, keeping 500 conformers, the lowest and the best 500 conformers within 40 kilojoules. We'll do a geometry optimization with the Hartree-Fock model, not because it's a terribly good model, but this essentially gets rid of duplicates. And mechanics tends to hold on to some duplicates that are available based on you know, symmetry and other features. And once we run that Hartree-Fock, we get rid of those. We keep 200. Then we do a density functional energy calculation. And this is really the first time we really prune things down to only 100 conformers. We further do a geometry optimization at a density functional model. And this is actually where the NMR calculation is done. And then based on those structures, we do an additional energy calculation with that larger basis set and the better model, or the more time-consuming and more accurate model, the XD model that I mentioned earlier in the properties dialog. And we base the actual Boltzmann distribution that we keep on the energetics from this big basis set, good density functional model. And the recipe is customizable, but this is the default that we do. And that actually, in addition to the empirical corrections that we have in place for the calculated carbon spectra, we also take into account the Boltzmann weights of the contributing conformers, and that makes a significant difference in the actual results as well. I mean, NMR is a long experiment, so you actually do have contributing conformers that make a difference in the results of the experiment, and we can take those into account with regard to calculation as well. So I'm very pleased with the level of results that we've been able to achieve with calculated NMR at this point, and we'll have a paper that I'll let you tend to know about once it's finalized. But we may have submitted it already. It's going to come out in the Journal of Natural Products. We've done a lot of consulting with a couple of different natural products groups in Japan on using calculation to assist with assessment and assignment of NMR spectra, and results look promising at this point. So I've taken up a good chunk of your evening. We've done a lot with regard to building. We've done a lot with regard to looking at some means of accessing data, whether it's from the properties dialog or from the output. We've only done a tiny bit with regard to calculation. We ran a single equilibrium geometry calculation. We haven't touched on things like reactions or transition states. We haven't looked at anything like any similarity analysis. I retrieved but did not run an NMR calculation. I've just roughly referenced that. I want to point the group, and I'll do it afterwards via email as well, to a menu that we haven't referenced in Spartan yet, and that's the activities menu. And under the activities menu, if you click on tutorials, I have basically taken us through 1, 2, 3, 4, 5, about the first 6 of these. There are many more examples in these first 6 tutorials, but I've essentially touched on about the first 6. There are an additional 7 or 8 that I would definitely encourage you to peruse. Each one is an individual PDF file. So if I click on one, that's just gonna, you might not see this, but it will open up a PDF file. I'm only screen sharing the Spartan interface, but it will open up a PDF file directly associated with that specific topic. Also, the full menu is available under the help menu, and this manual will include all of the tutorials, but also has the sets of topics and then a full user guide. So those are good places for additional reference. And then there's one last piece I wanted to point to. It's actually it's kind of a horrible dialogue, only because it's just very big. But if you click on the options menu and then hit what's called preferences, this is a tab dialog. This encompasses essentially all of the user preferences for the Spartan interface. So in the beginning, we talked about the 3D building, and we pulled up the model kit, and I said that the ChemDraw interface isn't turned on by default. So if you look down here towards maybe a third or 2/3 of the way down, under miscellaneous, there's a ChemDraw interface. So because this box is checked, that little interface box appears, or that little interface tab appears in the model kit for 3D. There's a whole host of options that are available under preferences. If you were going to customize the icons, there's a default set of icons that we show, but there are many more that are available to turn on as permanently displayed. All of the icons are available under the menus, though, so you really only need to do that if there's something that you feel is missing that you are going to reference very often. The molecule tab is something that will reference the preferences for molecules. So things like labeling, all of this is basically pre-configured to assist you, but the default atom label will appear. But if you wanted the default to be the electrostatic charge, for example, or if you wanted the default to be a mass number or a calculated shift, that would be the default label that appears when you turn labels on. So there's a host of additional functions that are available. So if you get to the point where you're using Spartan, you're like, man, I really wish I could see this, or how come I can't easily access that? it's very likely that there's a user preference that's available. That's well documented in the manual, but you should always feel free to send an email to us via support@wavefund.com. And if you got a question that you just can't figure out, but based on using the program, or you tried to search the manual and you couldn't find what you were after, send us a note and we'll be happy to follow up. We're typically no longer than a 24-hour response time. And if you hit us during our business hours, which are going to start not for another 2 hours here, we'll try and cover it the same day. At this point, I'm going to wrap as far as the presentation point is concerned. So I'm going to stop the recording. But what I will do is I'll stay on the line and cover any questions that you may have.